Hello, scholars. It's me, Miss Bland, and today is Thursday, August 27th of 2020, and today we'll be talking about chemical formulas. We have two objectives today. Our first objective is that Knights will be able to interpret chemical formulas, and the second objective is that Knights will be able to identify the elements that make up a molecule given a chemical formula. So before we jump into chemical formulas, we need to talk about the difference between atoms and molecules. Atoms are the basic building blocks of matter. If I took any sample of matter, take wood for example, and I zoomed in to see what it was made out of, the smallest thing that I would find is an atom. Each type of atom or element is documented and organized on the periodic table like we looked at on Monday. Here are a couple examples of atoms. The image on the left is a more accurate representation of what we think an atom probably looks like. It's definitely not perfect, but it's pretty close. On the right side, we have a diagram that shows the parts of an atom. At the very center, you have the nucleus, and that's where the protons and the neutrons are. Around the outside, you have what's called an electron cloud, and that's where the electrons are sort of hovering around the neutron. So an atom is just one single unit. It's one individual piece of matter, and it is the most simple piece of matter. So molecules are when you have one or more atom that's chemically bonded together. A molecule can contain any number of any element. Here are a couple of examples. The molecule on the left is a water molecule. The red atom is an oxygen atom, and the two white atoms are hydrogen atoms, and those bars in between represent the bonds that hold those atoms together. On the right side, we have a much more complex molecule, likely containing carbon, oxygen, and hydrogen. Now, both of these examples are compounds. In fact, every molecule, almost every molecule is a compound. If a molecule contains more than one type of element, then it's a compound. So now let's move on to chemical formulas. Here are a few examples of chemical formulas. A chemical formula is a set of chemical symbols that represent the elements present in a compound and their relative proportions. So relative proportions meaning how many of each element there are in that particular compound or molecule. In chemistry, we use chemical formulas all the time, mostly to represent molecules, but also to represent entire chemical reactions, which we'll look more at tomorrow. So there are three main parts in a chemical formula. You have the symbol, the subscript, and the coefficient. So let's start with the symbol. These are not all of the symbols that are in these three examples, but there are some of them. Now, these symbols can all be found on the periodic table. That's exactly where they come from. And it's important to remember that a chemical symbol will never be a lowercase letter. You'll notice in the first example, we have a capital C and a capital O. Those are two separate elements because they're both capital letters. Same thing in the second example. A capital H is its own element and a capital O is its own element. But in the third example, we have NaCl. This one is different because the A is lowercase and the L is lowercase. As I just stated, a lowercase letter by itself is never going to represent an element. So if there is a lowercase letter, it has to be sort of connected to the capital letter that's in front of it. So this lowercase a, because it's lowercase, it is part of the capital N. That's all one chemical symbol, and that's the chemical symbol for sodium. The lowercase l can't be its own element, so it's paired with the capital C. And capital C, lowercase l is the chemical symbol for chlorine. The second part is the subscript. These small numbers are the subscripts, and this indicates the quantity of atoms of a particular element. The subscript, you'll notice, comes after a letter or after a chemical symbol. So in this first example, that little 2 that follows the O is telling me that there are 2 atoms of oxygen. In the second example, that little 2 that follows the H tells me that there are 2 atoms of hydrogen in just one molecule. The last part of a chemical formula is the coefficient. The coefficient indicates the quantity of the molecule that immediately follows it. So in the second example, we have 2H2O. That coefficient is telling me that there are 2 H2O molecules. In the third example, the 3 in front of the formula is telling me that there are 3 molecules of NaCl. So today in your practice, you are going to be given a chemical formula like this one. You will need to identify the elements using the periodic table, and you will need to identify the quantity of each. So I will show you how to do that with a few examples. In this example, we have 2H2O. H is hydrogen and O is oxygen. So in your table, you're going to put hydrogen and oxygen. So now I have to determine how many there are of each. I like to ignore the coefficient at first and first figure out how many I have of each individual element. We know that this this subscript applies to this too, but you'll notice there's no subscript after the O. That means that there is only one O. It's tempting to think that that might mean that there are 0 atoms of oxygen, but if there were 0, then there would be no O on this chemical formula at all. So if you have a chemical symbol and there's no subscript after it, you can assume that there's a small invisible 1 there. So now I know that I've got 2 hydrogens and 1 oxygen in each molecule. But this coefficient tells me that I have 2 molecules that look like that, 2 molecules that have 2 hydrogens and 1 oxygen. So I still need to figure out how many of each atom there is total. And to do that, I will take this 2 and multiply it by each subscript. When I multiply this coefficient by this subscript, I'm finding the number of hydrogen atoms there are, which is 4. When I multiply the 2 by this 1, I'm identifying how many oxygen atoms there are, which is 2. I can draw out these molecules and I should end up with the same thing. In one molecule, I've got 1 oxygen atom. Let's say this pink color is oxygen. And I have 2 hydrogen atoms that are bonded to it because there is no space in between the H and the O. My coefficient says that I have 2 of these. So I'll draw another one. It's not exactly the same color, but it's fine. Okay, so now that I've drawn out these atoms, I can just count. I can see that I have 1, 2 oxygens and 1, 2, 3, 4 hydrogens. So I still have the same answers no matter how I decide to do it. Okay, let's do another example. we have CO2. If I look up C on the periodic table, I'll find that it stands for carbon. And if I look up O on the periodic table, I'll find that it stands for oxygen. This time, let's draw it out first and see what we come up with. Let's say this dark blue is carbon. So since there's no subscript after the C, I can assume there's a little invisible 1 there. Sorry, that one is ugly. It's fine. So I only have 1 carbon. Since I have a 2 right after this oxygen, I know that I've got 2 oxygens. And I don't have a coefficient, so that means I only have 1 of these molecules. So my answer should be I have 1 carbon and I have 2 oxygens. Okay, third example, I have 3 NaCl. If you look up Na on the periodic table, you'll find that it represents sodium. And if you look up Cl, you'll find that it represents chlorine. This time I don't have any subscript, so again, we're going to write in these invisible ones right here. If I ignore my coefficient for now, I can see that one molecule has 1 sodium atom and 1 chlorine atom. However, this coefficient is telling me that I've got 3 of these. So if I draw out my 3 molecules, I can count my molecules of each. I've got 3 pinkish red ones. Let's say those are my sodiums. And I have 3 yellowish green ones. Let's say those are my chlorines. I would get the exact same answer if I use the multiplication technique. I take the 3, multiply it by the subscript to see how many NAs I have. So 3 times 1 is 3. Take the 3, multiply it by the chlorine to see how many chlorines I have. 3 times 1 is 3. My answers are exactly the same. Okay, let's do one more. This one does have a coefficient, which is 2, so we're going to ignore that for now. And every single element here has a subscript already. So I've given you the elements. It's carbon, hydrogen, and oxygen. In this case, the multiplication technique is much easier than drawing because this is a lot of atoms to draw. So again, we'll take the coefficient, multiply it by the subscript to see how many carbons we have. So 6 times 2, and that's 12. We'll take the coefficient and multiply by this subscript to find out how many hydrogens we have. 12 times 2 is 24. And again, we'll take the coefficient, multiply it by the subscript 6 to find out how many oxygens we have, and 6 times 2 is 12. And that's all there is to it.